Students, I am Raghavan, chemistry faculty from ALPHORES colleges. I invite you all for the ALPHORES chemistry e-learning classes, session 38. Okay, in the last session, that is in the 37th session, we started 1A group, that is S block elements. Under this alkali metals we started. So in the last session we completed electron configuration of alkali metals, and we had some physical properties such as atomic radius, ionization energy, electronegativity, electron affinity. So these physical properties we completed. Okay, and now today we are discussing about another concept, that is general physical properties, that is general properties only of alkali metals, 1A group elements, general properties of 1A group alkali metals. Okay, that is density of the elements, okay. So the density of the elements, so density is equals to, what is the general concept? Density is equals to mass by volume. That means as atomic mass increases from top to bottom, densities also increases because they are directly proportional to each other. So from top to bottom, density increases from top to bottom, okay. That is a common concept. Density increases from top to bottom in the group, okay. From top to bottom densities increases, okay. That is a general concept. So that means the density of, we have lithium, sodium, potassium, rubidium and cesium, because francium, we know that francium is being radioactive element, so the properties we cannot discuss about up to francium element, so we will discuss only up to cesium, okay. So the properties we have to discuss from lithium to cesium only. So densities from top to bottom, as atomic mass increases, so densities also increases. That is a common trend. But the important point is, see, the density of potassium supposed to be greater than sodium, but density of potassium less than sodium, that is only the important point with the reason concept, okay. That only point we have to explain, okay. So why the density of potassium is less than, it's supposed to be greater, but it is less than sodium. Why the density of potassium is less than sodium? Yes, so density directly proportional to atomic mass and inversely proportional to volume of the element, okay. Due to the presence of vacant 3d orbital, when you observe that potassium atomic number 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So in 3d orbital, that is in the third energy level, the d orbital is completely vacant, okay. You have to recognize that. So due to the presence of vacant 3d orbital, the atomic volume of potassium is suddenly increased. So because of the large atomic volume, its density is less, okay. The density of potassium is less than sodium due to the large atomic volume, due to the higher atomic volume, due to the presence of the vacant 3d orbital. This attributes the less density of potassium. You got it? Okay, that is the important point. The density of potassium is less than sodium due to the presence of vacant d orbital, vacant 3d orbital. Due to the presence of vacant 3d orbital, the atomic volume of potassium is greater. That is why its density is less. Yes, that is the important point. So density is done. Important point. That is, this point is only the important point. Okay, that is density concept. Okay, now the next concept, let us proceed. But overall density is, so density, this is a common concept, that is density is equals to mass by volume. So from top to bottom, as atomic mass increases, densities increases down the group, but the density of potassium is less than sodium due to the presence of vacant 3d orbital. The atomic volume of potassium is greater, okay. Yes, after this density, the next one is see, in the last class we had See, alkali metals can be stored because they are highly reactive. So that is why alkali metals are stored in kerosene, we said. Okay, but lithium is lighter than the kerosene element. Lithium is lighter than the kerosene. So that is why lithium can be stored in paraffin wax. Okay, it is stored in paraffin wax. That is the point you have to remember. Except lithium, the rest of alkali metals are stored in kerosene. Why lithium cannot be stored in kerosene? Because lithium is lighter than the kerosene. That is why it floats. That means again it is exposed to the atmosphere. So that is why lithium is stored in paraffin wax. Okay, that is the point. Yes. Storage. Last class only we completed. So once again today I reminded that so lithium is stored in paraffin wax and the rest of the alkali metals can be stored in kerosene. That is done. Next one is hydration energy. The next concept, hydration energy. Very important concept. Hydration energy. What is the concept of hydration energy and what is the significance of hydration energy in this group? Yes. Hydration energy. Suppose when a metal substance is added to the aqueous solution, hydration energy. Okay, hydrated means water. Okay, when a metal ion is added to the water aqueous solution, so what happens? This metal ion is surrounded by water molecules. The metal ion get hydrated by water molecules. Okay, so the amount of energy liberated, the definition of hydration energy, the amount of energy evolved when an ion get hydrated with water molecules. I repeat, the amount of energy evolved when an ion is hydrated with water molecules or hydrated by water molecules. That is called hydration energy. Now, hydration energy is inversely proportional to the size. Yes, this is the concept. Hydration energy is inversely proportional to the size. Okay, that means so smaller the size, higher will be the hydration energy. Okay, so therefore, so which ion gets more hydrated? So we have, so in aqueous solution, so lithium ions, Li, lithium ion gets more hydrated. So that is order of hydration energy. Okay, that is order of hydration energy. Lithium ion greater than sodium ions. Sodium ions gets more hydrated than potassium ions, K plus, and potassium ions are more hydrated than rubidium ions. Rubidium ions are more hydrated than cesium ions. So which alkali metal ions gets more hydrated? Lithium ions gets more hydrated. That means lithium absorbs more and more amount of water. What happens? So the hydrated lithium ion gets bigger in size. Okay, that means by absorbing more water molecules, the radius of hydrated lithium ion becomes bigger in size. So the radius of hydrated ions. Now what is order? The radius of hydrated ions, that is radius of hydrated lithium ion is much bigger than the radius of sodium ion. It is much bigger than the radius of potassium ion. It is bigger than the radius of cesium ions. That is radius of the hydrated ions. You got it? Is it, the concept is clear? Hydration energy inversely proportional to the size. So therefore, the smaller size alkali metal ion gets more hydrated. So lithium being smaller size, so therefore lithium ions gets more hydrated. Okay, then when lithium ions gets more hydrated, the size of the lithium ion becomes bigger in size. So that is radius of lithium ions are bigger than other alkali metal ions. Okay, now mobility of ions in the aqueous solution. Mobility of ions Mobility of ions. See, why the ions should mobile? Mobility of ions. Mobility of ions. Yes. See, this is hydration energy order. This is the radius of hydrated cations. Then, see, conductivity means what? Mobility of ions only. Conductivity. So, when aqueous solution of the salt solutions, aqueous salt solutions are present. So now conductivity means what? Mobility of ions. Conductivity directly proportional to mobility. Conductivity directly proportional to mobility. That means the ions move towards opposite electrodes. So if the ions are moving faster to the opposite electrodes, that is very good conductor. Okay. So that is good conductive nature. So now mobility is mobility of ions. Mobility of ions is inversely proportional to the size. That means smaller ions move faster, larger ions move slow. Okay, smaller ions move faster. This is the concept, we know that. Mobility of ions. Okay. Then smaller size, which is larger size. So in the aqueous solution, so lithium ions are very much larger in size and cesium ions are very smaller in size due to least hydration energy. So therefore mobility of ions, which ions will move faster? So now cesium ions. So the mobility of ions, cesium greater than rubidium, greater than potassium ions, greater than sodium ions, greater than lithium ions. So the mobility of ions, cesium ions move faster because of the small size. Okay, that is in aqueous solution. That is hydration energy. Hydration energy means now the ions are connected to water. You have to understand that all these concepts explained in aqueous solution only. So the hydration energy. Okay, the order of hydration energy, that is like this. Lithium ions gets more hydrated in aqueous solution because their size is very small. That is why hydration energy is more. So hydration energy in the aqueous solution. Okay, so that is in aqueous solution. Here I am mentioning clearly because hydration means it is already connected to water. Okay, so radius of hydrated ion, the radius of hydrated ion, lithium is bigger in size than sodium. So from top to bottom, as the size increases, hydration energy decreases, and therefore the smaller size lithium ion gets more hydrated. Therefore the radius of hydrated lithium ion is much more bigger than the other alkali metal ions. Okay, therefore the mobility of lithium ions is very less, very less. And so the radius of cesium ions, hydrated cesium ion, is very smaller in size. Therefore cesium ions move faster. That means mobility is very high for cesium ion. This is also in aqueous solution only. Okay, aqueous solution. Okay, that is the concept of hydration energy. Okay, remember that. Once again, hydration energy definition we have done. Okay, that is the amount of energy liberated when an ion is added to water. Okay, because that ion is hydrated with water molecules. So during the process, during the hydration process, the amount of energy liberated, that is called hydration energy. Okay, now, so hydration energy is inversely proportional to the size. Smaller the size, greater will be the hydration energy. Yes, among all the alkali metals, lithium is smaller in size. Therefore, lithium hydration energy will be more. That means lithium ions get more hydrated. Okay, so lithium, so among all the alkali metals, lithium chloride can exist as dihydrated molecule. Okay, that is another important question. So lithium chloride is hydrated with number of water molecules, 2, 4, 3, 6, 8, like that. So it is hydrated with 2 water molecules. That is important point. Lithium ions are hydrated with 2 water molecules. Okay, so the size of the hydrated cations are mentioned. Then mobility. What is the concept of mobility? That is conductivity is directly proportional to mobility. Okay, conductivity directly proportional to mobility. So mobility is inversely proportional to the size. Mobility is inversely proportional to the size. Smaller the size of ion, more mobile, easy mobile. Okay, therefore, so in aqueous solution, the radius of cesium cation is smaller. So therefore, the mobility of cesium ion is greater than rubidium, greater than potassium ion, greater than sodium ions, greater than hydrated lithium ions in aqueous solution. Okay, this is the concept of hydration energy, very important concept. Okay, the next concept is flame test. Next very important concept of alkali metals is flame test. What is the flame test? How we can perform that flame test? Let us see the concept of flame test or flame coloration test. So how we can perform that flame coloration test? See, now alkali metal or alkali metal ion compound, you can take suppose sodium, you can take sodium metal or you can take sodium compound, any sodium compound. It may be sodium chloride, sodium hydroxide, sodium carbonate, sodium bicarbonate, anything of sodium compound. Okay, that is alkali metal ions, they exhibits the characteristic flame coloration. Okay, they exhibits the characteristic flame coloration due to low excitation energy. Alkali metal ions exhibits the characteristic flame coloration. Okay, see, for example, suppose if it is a alkali metal, say for example sodium. Okay, and yesterday in the last session we had discussed that, so they possess the lowest exceptional low ionization energy. Okay, because they contain only one electron in the valency shell and their nature is electropositive. They always get stabilized by losing electron. Okay, so this unpaired electron, by heating this substance, what happens? So the unpaired electrons of valency shell can get easily excited. In the higher energy level, the electrons are unstable. Excited electrons are unstable in the higher energy level. They should fall back to the ground state. During this de-excitation process, they emit some radiation. The emitted radiation only we can find the color. Okay, that is the emitted light. So that is emitted light that gives all alkali metal ions gives the characteristic flame coloration test. Due to low or least excited energy. All alkali metal ions exhibits the characteristic flame test. That is the reason point. Okay, now sir, how we can perform the flame test? Let us see. That is in a watch glass. Let us take alkali metal or its compound. To this 1 drop of or 1 to 2 drops of concentrated hydrochloric acid is added, and with the help of a glass rod it is made into a pasty mass. That is alkali metal or its compound is mixed with 1 or 2 drops of concentrated hydrochloric acid. Then it is the pasty mass is taken on the glass rod and exposed to the blue flame of the Bunsen burner. It is exposed to the blue colored flame of the Bunsen burner. So in the Bunsen burner, the flame of the Bunsen flame, it changes to the different colors according to the nature of the element. Okay, so the characteristic flame test is observed. So now lithium exhibits the characteristic flame test, that is crimson red color. It shows crimson red color. That is lithium exhibits the characteristic flame test is crimson red. Sodium metal or sodium compounds exhibits golden yellow color. Potassium gives the characteristic flame test, that is lilac or we can say violet color. Okay, then rubidium is exhibiting red violet color, and cesium exhibits blue violet color. Okay, this is about the that is flame test of alkali metals. Okay, so flame test, why do the alkali metals gives the characteristic flame test? Due to low excited energy. Excitation energy of these elements is low. That is why they gives the characteristic flame test. All the alkali metals gives the characteristic flame test. Okay. So what is the color of lithium compounds? Lithium compounds gives crimson red color, sodium compounds gives golden yellow color, potassium compounds gives lilac, that is violet color, and rubidium compounds gives the characteristic red violet color, and cesium compounds exhibits the characteristic blue violet color. Okay, that is about flame test of alkali metals. That is flame test of alkali metals. Okay. So with this almost we completed the general properties of alkali metals. And another point, what is oxidation state of alkali metals? Oxidation state of alkali metals. See, alkali metals, as they are possessing only one electron in the valency shell, and by nature they are all electropositive, highly reactive electropositive metals. Therefore, by losing their valency one electron, then they acquire the stability of nearest noble gas element. Okay, therefore that means lithium, sodium, potassium, rubidium, cesium, in any of the compounds, that means in the combined state, they always exhibits only +1 oxidation state. In any of their compounds, any alkali metal atom always exhibits only +1 oxidation state. It may be oxides, hydroxides, halides, carbonates, bicarbonates, whatever the compound of alkali metal. In that compound, alkali metal atom always they exhibit only +1 oxidation state. Okay, only +1 oxidation state. Okay, that is the point, important point we have to remember. Okay, any compound you take, lithium compounds, sodium compounds, potassium compounds, rubidium compounds, cesium compounds, any compounds of the alkali metals, okay, alkali metal atom exhibits only +1 oxidation state. Right, that is about the concept of oxidation state. Why do they exhibit only +1 oxidation state? Because they possess only one valence electron. By losing its valence electron, they can acquire the stable configuration of the nearest noble gas. For example, lithium, by losing its outermost electron, it forms lithium +1 ion. So this lithium +1 ion acquires the stability of helium, and sodium can lose its one electron from its valency shell, then it forms sodium ion. It acquires stability of neon. Similarly, potassium can lose its one electron, then it forms potassium +1 and it acquires the stability of argon, like that. Okay, and rubidium can acquire stability of krypton, and last one, cesium acquires stability of xenon, like that. Okay, so since they contain only one electron in the valency shell, by losing one electron they acquire the stability of the nearest noble gas element. Okay, that is why all alkali metal atoms in any of their compounds, they always exhibit only +1 oxidation state. Yes, that is about the concept of oxidation state we have done. Okay, then melting points. Yes, another important point is melting point. Melting points of alkali metals. Yes, see, what is the nature of the alkali metals? Yes, all alkali elements are very strong electropositive reactive metals. Melting points, yes. So lithium, see, all alkali metals, but nature, all alkali metals can easily cut with a knife. Okay, alkali metals can cut with a knife, that means they are soft. They are all soft metals except lithium. Lithium is only the hard metal. The rest of the alkali metals are soft metals. They can be easily cut with a knife. Okay, so therefore, so lithium possesses high melting points. That means melting points of alkali metals gradually decreases from top to bottom. Melting points decreases from top to bottom. Lithium greater than sodium, greater than potassium, greater than rubidium, greater than cesium. Okay, melting points. Lithium, being lithium is hard metal, so it can be easily cut with a knife. That is melting points of alkali metals. So that is completed. So now we almost completed the general characteristic properties of alkali metals. Okay, now let us go with oxides, that is chemical properties. Chemical properties of alkali metals. Chemical properties. Chemical properties, yes. Chemical properties of alkali metals. First one is oxides. Oxides. Alkali metals can form M2O type of monoxides, M2O type of monoxides, M2O2 type of peroxides, and MO2 type of superoxides. It is oxides. Oxides, and they are peroxides. Peroxides, and they are superoxides. Superoxides. Oxides, peroxides, and superoxides. Yes. What is the formula of oxide? Oxide ion formula is O minus 2. That means oxidation state of oxygen atom is minus 2. So what about metal ion? So the metal atom is always exhibit plus 1 only. Alkali metal atom in any of the compound always exhibits only plus 1. Plus 1. Here also plus 1. Okay. So oxide. Peroxide formula. Peroxide formula is O2 minus 2. That is peroxide. This is oxide. This is peroxide. And superoxide, it is O2 minus 1. O2 minus 1. That means oxidation state of each oxygen atom is minus 1 by 2. That is the point you have to remember. What is oxidation state of oxygen atom in superoxide? It is minus 1 by 2. So oxidation state of oxygen atom in the peroxide, it is minus 1. Peroxy bond, it is minus 1. Here oxidation state is minus 2. Okay. So that is the formula of oxide. The formula of oxide, formula of peroxide, the formula of superoxide. So among them, superoxides are paramagnetic in nature. Superoxides are colored and paramagnetic. Superoxides are colored and paramagnetic. Paramagnetic. That is one important point. Colored and paramagnetic in nature. That is about introduction to the oxides. Okay. Now, let us take up oxides. Okay. Now we have to start oxides. कितने हुआ? That is monoxides. Oxides of alkali metals, that is they form M2O type of monoxides. Monoxides. That is formula is lithium monoxide, so sodium oxide, that is all oxides. Okay, lithium oxide, sodium oxide, potassium oxide, rubidium oxide, cesium oxide. Okay, cesium oxide. These are all oxides. Okay, that is all alkali metals can form. All alkali metals can form monoxides. Okay, what is the nature of these oxides? Nature of the oxides. So metal oxides are always generally basic in nature. Metal oxides are always basic in nature. So which is more metallic in nature? So metallic nature is directly proportional to electropositivity. Okay, that means electropositivity, that is cesium is more electropositive metal. So therefore cesium oxide is strong basic nature. Okay, that is nature of the oxide. Basic nature. Basic nature of the oxide. Basic nature of the oxide increases from top to bottom with increased atomic size. So therefore we can say lithium oxide is less basic than sodium oxide. It is less basic than potassium oxide, K2O. It is less basic than rubidium oxide, and it is less basic than cesium oxide. Cesium oxide is strong basic oxide. Strong basic oxide. That is basic nature of the oxides. Okay, then when cesium oxide is strong basic in nature, then what is the solubility of these oxides? solubility of the oxides also increases from top to bottom because it is strong basic in nature. Okay, that is strong basic means what? So what is the meaning of strong? That means they possess high degree of ionization, or you can say high degree of dissociation. The substance which possesses high degree of ionization or high degree of dissociation is called strong. It may be acid or it may be a base. Okay, being it is a strong base, so the cesium oxide possesses high degree of ionization in water, so therefore it forms a strong basic solution. So therefore that is the solubility of the oxides increases from top to bottom. Solubility increases from top to bottom. Solubility increases from top to bottom. Lithium oxide is less soluble due to highest lattice energy. Okay, so highest lattice energy, lithium oxide is less soluble in water, so from top to bottom lattice energy decreases and basic nature of the oxide increases. Therefore cesium oxide is more soluble. Cesium oxide is more soluble and forms a stronger basic alkaline solution. Okay, stronger basic solution means alkaline solution. Okay, that is solubility. Lithium oxide less than, solubility of the lithium oxide less than sodium oxide, less than potassium oxide, less than rubidium oxide, and less than cesium oxide. So cesium oxide is more soluble in water and forms strong basic solution, that is alkaline solution. Okay, and we have stability also. Stability, okay, stability of these oxides. So stability also increases from top to bottom. As the atomic size increases, stability of the oxide also increases. So cesium oxide is more stable. Okay, that is stability also increases, basic strength increases. Okay, so solubility also increases down the group.